All right. Okay, so I sent out this syllabus. Yes. Any questions from that? Did you all get a chance to read it?
Yeah, the bottom of the first page, the ear training thing.
Ah, yes. You wouldn't know about this. So there's a little Blackboard thing that I need to enroll you in. Called Golden Ears. And this is the David Moulton Golden Ears training. So every week you have to log on, and there's usually 2 little drills. So what happens is you put on your headphones, or monitors are better, and you just listen. He's going to give you something to listen to, and you have to guess what it was. So this semester we're doing reverb. So we're guessing pre-delay times and reverb tails. Okay, so you'll hear it. You listen to it as many times as you want, and there's a menu where you select what pre-delay was and what the reverb time was. And so there'll be like two sets of 10. But take you what, 10, 15 minutes to do these? Yeah. So you just do that once a week. And that's not. So I'll enroll you right now. Actually, while I'm thinking about it, or I will forget.
Is that a new thing? Adding golden ears to the
No, it is not new. I do it for every one of my classes.
No. I was meant like it's a requirement. Like it's
Yeah.
grade.
Yeah. Well, it is for me. I don't know how David does it, but. Okay, let's see. Remind me your last name, Jim.
SCHMEFEL.
All right, let's see if that. No, SCH. Let's see if you're in here. I got a John Schimmel, Corey J. Schiffhauer. It appears you may not have an account on it. Have you ever used Blackboard on campus yet? Do you know what's your email username?
Schneifel.jm.
Oh, I have it actually. Let me put that in. Come on. Let's see. Syllabus. Ah, there it is. There you are. Okay, you're in. All right, so what happens is when you go in there, it'll take you to this page, and it'll look like this. And so I try to do it's fun. We compete against each other. So I'll do a top 10 scores, and I'm supposed to do it every week. Sometimes I forget, but so every week a new little folder will pop up. So this is week 73. We'll go up there and reverb drill. You start it, and here they all are. Oh, they do. Oh, sorry. I'll work on that. But at any rate, you listen to them. Turn it up and you can hear it. So these are kick drums. Oh, why is it scrolling so far? Look at that. Has it been doing that for you guys too?
Yep.
All right, I'm going to have to look at that. So we're supposed to do it vertically. Anyway, so you've got your options are pre-delay 0, reverb time 03, so on and so forth. Let me listen to see if I can guess. So that is something in the range of 80 and 3, I think. 80 milliseconds pre-delay, 3 seconds reverb time, something around.
Is there a demo example?
Hmm?
Is there a demo example?
There was last week. Did you skip last week?
Yes, I did.
Oh my goodness. All right, I'll turn it back on. So let's see, that would be week 72. So I'll go through and figure out why those are scrolling that weird way. Week 72. There you are. Criteria, date, edit, display until, let's see, today is the 23rd, so I'll let you see it until end of next week. How about that? Okay. All right, so go through that. Anything else? Any other questions from the syllabus? So anyway, you do that every week. If you miss, it's not the end of the world. What happens is, and it has nothing to do with how good you do. Right? The scores are not the point. The point is that you do it. Okay? So you either did it or you did not do it. So at the end of the semester, I just say, all right, it's 15 weeks. So I look at each of those 15 weeks. How many of those 15 weeks did you do it? And if you did it 15 weeks, then you get full credit for that particular 10% portion of the grade. Okay, so missing 1 week, for example, is not the end of the world. That is ultimately doesn't even take you down. Would take you down to like 93% for golden years, which only counts for 10% of your grade. So this is not the end of the world, but you should do it. If you completely blow it off, that's a letter grade, right? Okay. So don't completely blow it off, but don't kill yourself if you forget 1 week. It's not the end of the world. Anything else? There's no textbook you need to buy. The only thing we're gonna do is my book, which actually we finished. I did one last push over the Christmas break, and it is done. So here you go, digitalsoundandmusic.com. Okay.
With games.
With fun games. We'll do some of the games. Okay. And actually, if you go to the curriculum menu here and go to curriculum modules, I've actually made a little module for our class. This one in the middle, sound design technology. And that has all the stuff that we'll look at all just on one page. Okay, so you don't have to go hunting for it. So all of the reading is all bundled together into one thing. Because there's stuff that in the book that has nothing to do with our class. So this first thing is all the reading assignments. So if you hit this little read it button, you'll get, this is all of the stuff I'll have you read over the course of the semester. Okay, and I've indicated in the syllabus where those are. Okay. It's just supplemental stuff that you can read. But then also all the demos and stuff that are a lot of fun.
What was the link that you clicked into? Was it like under curriculum?
Curriculum modules,
Yeah, I see.
and then it's there. You can also find them yourself. Just there's a, when I say, go look at this demo, you can go find it on here if you would go to, and if you want to look at some of the others, you can. So there's the learning supplements, for example. And if I say, oh, go look at this Flash demo, so you would go to the Flash tutorials, and here's where they all are. But there's a lot here that don't have anything to do with our class. But, so for example, one of the ones that we'll look at next week is the audio signal path, which is this one. New intro music. Yeah.
It's super fancy for me.
So this we're going to talk about this in next week for next Friday. So this is all the different. It's an examination of okay, what's happening when sound is happening on a computer. What does that mean? What are all the different steps involved in that? And so we're going to zoom in. So for example, here's the analog to digital converter, and it explains, well, what does the analog to digital converter do? It does this thing. And then there's the actual controller for the sound card. There's the RAM buffer on the input. What does that do? And okay, so they're fun. Some of them are fun little games you can play and things like that.
Oh, there's so many interactive things.
Okay, but so this is why we didn't publish this thing printed in a piece of paper, because
This is really awesome.
there's not all that much stuff that's useful on a piece of paper that we wrote. So anyway, there are things you can read, but the far more interesting stuff are all of these supplements. Okay, and we'll go through some of them in class. Not today. I think next week we'll start looking at them. So anyway, that's there. I've shown you how to get to that. The culmination of the last 6 years of my life, by the way.
Ooh.
It's gonna get
I know where all my free time is going now.
Yeah.
Like,
Okay, that's it, I think, for the syllabus. Any other questions about that? No? Okay. Great. So today we're going to talk about computers. So generally, that's kind of the subject this semester. Okay, we're talking about computers and how we do sound with them. But before we can learn how to do sound with them, we have to sort of just learn how they work to begin with. And let's see if I can pull up some notes here. So today is really not about sound. Today is just about computers in general. How does a computer work? And you need to understand. I know you all think you know how these things work.
no, I don't.
But you would be surprised at what you don't know. Oh, right, I don't have that thing working. So, but let's talk about what computers actually do. And if you ever go into, if anybody ever taken a beginning computer science class? Okay. So they talked about what computers do. You remember what the 4 things are that computers do? Okay. They would have made you chant it, probably as a big group. Usually, I don't know. That's what they did when I took those classes.
Things have changed since.
Things have changed, I guess.
You can make us process and make us chant it.
Yeah, I'm going to make you chant it. So here are the 4 things. The first one is input. Yeah, okay, okay.
Oh, okay.
Yes.
Great. Yeah, they never know. How was you making that up?
Input, output, processing, and storage.
Oh,
Okay?
that's right.
Right. Those are the 4 things that computers can do.
Okay.
They can't do anything else besides those 4 things. So we're going to talk about what those 4 things mean. As soon as I find my notes, here we go. So let's talk about input. What does it mean what do we mean when we say that a computer can do input? Well, a computer can, when we're talking about input, we're saying this is where the computer accepts information from the outside world. Okay? And it does that by collecting information from you, the human being, the person using the computer. So there's various ways that it can collect information from you. For example, the keyboard is a way that the computer collects information from you, right? As you push little keys on that keyboard, it's able to know what letters you would like it to do something about. Okay. The mouse is an input device, right? As you move the mouse or the trackpad around, that's how you input information to the computer about what you're wanting to focus on, okay, or interact with. Other input devices are things like a scanner, right? That's an input device. That's how you could, the computer could collect some sort of visual information from you. A camera could be an input device. If for some reason the computer needs to see your face or see the room you're in or whatever, that's a way it could collect things from the input. So on and so forth. Input devices for us related to sound would be things like microphones that would talk to, the actual input device would be the sound card, the audio interface. That would be your input device, but that's how it could collect sound from the outside world. Your MIDI keyboard, that is an input device. All right, as you push keys on that, you're putting information into the computer. The other sort of input that we talk about in computers is where the computer collects information from other computers. Okay, so and that's where you get things like the networking, internet, Bluetooth, Wi-Fi. These are all ways that the computer could collect information from other computers. Okay, and like your phone is another little computer, and there are ways that you can send information from your phone to your computer, your desktop computer, your laptop, right? And that's a form of input. Okay, there's your computer is receiving input from some other computer. Okay, that's what input means. All right, what does output mean? Well, output is the opposite. So this is where the computer communicates information out to the world. And it could communicate that information to the human beings, in other words, you, and it does that through output devices. that can send you information, things like the display or the screen on your computer. That's a big way that it outputs information to you. That's probably the one you interact with the most. Okay, but even a printer, that is an output device of a computer. It can output information to you onto a piece of paper. Okay, but things like a loudspeaker that's built into your computer, that is an output device. It could play you a sound that could tell you something, and that's something we do a lot, right? So anything that involves the computer telling you something, that's output. That's the computer outputting information to you. And it can also output information to other computers, using all those same tools that it used to collect information from other computers. So it could send information to your phone, or send information to another computer on a network. We do that a lot, don't we? When you're down at a tech table with your laptop and you're remoting in to the playback computer to either transfer files or control it, remote control QLab or something. I mean, that's where you're doing both input and output between two computers. And there's all kinds of input and output happening between those two computers that you don't even see. They're talking away to each other in ways that you don't even understand. So that's a whole other language it's talking that doesn't have anything to do with you, but that's a form of input and output. Okay, so we've got through half of the job of the computer, input and output. Those are two things that a computer can do. The third thing is processing. What does that mean? Well, this is where the computer performs. It can do there's two forms of processing it can do. It can do arithmetic or logical operations. So arithmetic meaning it could add 2 plus 2. Or it could perform some sort of logical operation where it could say true or false, or right or wrong, or yes or no. Okay? And that's it. Okay? Everything that has to happen on a computer has to ultimately be boiled down to either 2 plus 2 or true or false. Okay? It's the only kind of processing that the computer knows how to do. And we'll see as we go through here what that means. This is done with this thing called a CPU, Central Processing Unit. It's a little chip, and we'll talk about more in a minute. But it's what does the processing. Okay, storage. This is the fourth thing a computer can do. So the storage is where the computer can move and store information around at various spots on the computer, and we call that memory. There are two sorts of storage. There's primary storage, otherwise known as RAM. Okay, this is where the computer really prefers to put things. That's the primary storage location that it would really like to use for reasons we'll talk about in a minute. And so this is where the computer puts and stores things that it needs instant access to. So if it needs to be able to get at something really quickly, it really is going to want to put it in primary storage or RAM. There's also secondary storage devices. This would be things like your hard drive, the USB flash drive that you put in the computer. These are all secondary storage devices. The computer prefers not to use those for reasons we'll discuss in a minute. So that's why we call it secondary. So if for some reason it can't use RAM to store that, it's going to put it in the secondary storage. And this is the reasons that it would put something in secondary storage is if it had to remember it for a long time. So one of the knock-on effects of being able to get at it really quickly in RAM is that RAM can't remember it for very long. Okay? Whereas your secondary storage devices, like your hard drive and your USB thumb drive, it can remember stuff for a very long time, forever, theoretically. Whereas RAM is the complete opposite of remembering something forever. It remembers something only for a very, very short amount of time. Okay, so that's it. Those are the four things that a computer does. And we could diagram this. So this is the system diagram for every computer in the world. Okay, that's it. That's all you got. There's nothing mystical going on here. Four things: input, output, processing, and storage. So over here on the left, we have the computer collecting information from you or other computers, and on the right, we have it outputting information to you or to other computers, and then it's storing that information either in memory, RAM, or secondary storage, and that the CPU is at the heart of all of that. And that's where the processing happens. So as information comes in through the input devices, the CPU decides what to do about it. Right? And I says, well, I get to put that over in RAM for a minute, and then I'll think about it, and then I'll spit it out to an output device, or maybe I'll save it onto a secondary storage device or whatever. But the CPU is sort of the central hub of that whole thing. But that's it. Every computer is that. Okay? Got it? It's really not that tough. Really not that much going on. Okay? All right, let's talk a little bit more about this thing called the CPU. It stands for Central Processing Unit. Every computer has at least one of these, or it's not a computer. Okay? A lot of computers these days have more than one of these. Your laptop probably has a couple of them. My computer here my laptop has 8 of them.
Is that what the core is?
Yeah, so a core would refer to how many processing cores are in there. And ultimately, the real purists would say, wow, it's only one unit though, right? It's only one CPU, but it has multiple processing cores in it. But that is effectively another CPU, okay? But that when you say multi-core, that's what's happening, is you're adding processors to it. But you got to have at least one, or it's not a computer. My watch has a CPU on it. This watch is a little teeny tiny computer. It's a very, very small, very, very slow CPU, but it's a CPU nonetheless, okay? And as I said, this CPU it can do 2 things. It can do arithmetic, and it can do logic. That's it. That's all it knows how to do. So 2 plus 2, or true or false. And it communicates with all the other parts of the computer. So anything that happens on the computer ultimately has to go through the CPU, and it's housed. The CPU sits on a chip. The chip that sits on a little motherboard with a bunch of other stuff. Okay, so here's a motherboard, an old one. The CPU would go here in this one little brown slot. It would sit on a card and it would pop in there. Okay. Nowadays, it drops into a little. It's more. The slot is actually captive in there, and you drop the chip right in there. But this one, it would go onto a little card, and then the card would go into the slot. Okay. And then all these other things have to do with the different input and output storage devices. Okay. So when you talk about a motherboard, you're talking about the thing that contains the CPU and then some way of interfacing with all the other devices of the computer. Okay, so what's this important stuff you need to know about a CPU, aside from that it can only do arithmetic or logic? Well, there are 2 main factors with the CPU that you want to be aware of in that, and those 2 main factors are compatibility and speed. So compatibility, what I'm talking about there is software. So not all software is compatible with every CPU. So CPUs are generally designed in families or categories. So for example, there's 2 popular categories of CPUs. There's a PowerPC type of CPU, and there's an x86 type CPU. PowerPC is really found a lot in embedded devices. Your car probably has several PowerPC processors in it. Used to be in the old days, that's what Macs used. Macs ran on PowerPC processors. And then, I don't know, like 8 years ago or something, 7 or 8 years ago, they switched over to x86 type processors.
Like 6 years.
Yeah. And so there are fundamental operating principles behind each processor. The third one that isn't on my slide is called the ARM type processor. That's what's in like your phones. So like my watch has a little ARM processor. The Apple A4, A5, A6 processors, those are ARM processors. You don't need to know a whole lot about how they work other than knowing that software that is written for a PowerPC processor will not run on an x86 processor or an ARM processor or whatever other processor you use. The software is ultimately compiled and written for a certain processor. However, software can sometimes overcome its own compatibility problems. which is kind of interesting. So back in the days when Apple was using PowerPC processors, there was this company that created this product called Virtual PC. And it was this amazing piece of software that pretended to be an x86 processor. It's sort of like Parallels, but different. The Parallels uses this feature called virtualization that's actually built into the CPU. But what this was doing is this was a piece of software that pretended to be an x86 processor. And you could then run x86 programs on a Mac, and it would live translate the code. It would translate the machine code into a format the PowerPC processor could understand. And then you could run like Windows programs. It's really slow because, you know, all of that work that the CPU had to do to translate that code live, that was like very little left over for it to do anything else. So you had to really, really want to run that Windows program. But software can overcome that. So yeah, nowadays though, so for example, the chips that are in your Mac now are these, Intel makes these chips now that have this virtualization feature, and all that, what that's really doing is the machine code isn't changing. It's the same processor, because now, you know, the Windows machines and Macs, they're using the same processors now. What it's really doing is overcoming operating system issues. Okay, so the machine code down at the CPU level is the same. But what it's doing is virtualizing the operating system. So it's able to kind of pretend to be more than one computer at a time. So instead of pretending to be a different kind of computer than it is, it's just pretending to be like 2 computers or 5 computers, or however, you know, and the CPU is able to kind of direct that traffic and say, all right, I'm pretending to be 2 things at once right now. But the machine code is the same. So this is an issue with CPUs. You know, can't run every piece of software on every kind of CPU, and that's important. The other thing is speed. So one determining factor of a computer's of a CPU is its speed. How fast is it? And one of the ways to look at that is its clock speed. So there's this internal clock where essentially this thing is ticking, and every time it ticks, it can perform some kind of function. So every time it ticks, it can do a math problem. It can do 2 plus 2, or it could do true or false. And it can do that a certain number of times every second. And that's measured in like a frequency. So, for example, you know, your laptop might have like a 2 gigahertz processor, 2 gigahertz CPU. Gigahertz meaning it can do on 3 billion, it ticks 3 billion times a second or something like that. Isn't that what it?
2.6 billion times a second. Yeah.
So 2.6 billion times a second, that processor can do 2 plus 2 or true or false. That's a lot. That's pretty fast. I mean, you gotta give it some credit there. Okay, that's pretty cool. And for a long time, the goal was, all right, we got to make that clock tick faster. How many more times can we make it do something in a second? But that can be somewhat misleading. That isn't necessarily how fast it can work for you. For example, and these are relatively recent processors. So a 2.5 gigahertz Celeron CPU, not CPE, is not necessarily faster than a 2.1 gigahertz Core 2 Duo processor. Okay. So just because the Core 2 Duo is 2.1 gigahertz, which is a little bit slower clock speed than 2.5 gigahertz, that Core 2 Duo is probably going to be able to do some things faster. Why? Because it has 2 coprocessor cores in it. So every time that the clock ticks on the Celeron processor, it's doing one thing. But every time the clock ticks on that Core 2 Duo processor, it's doing 2 things. Or it's capable of doing 2 things. Right? It's not necessarily doing 2 things, but it's capable of doing that. If the software could be written in such a way that the CPU could do 2 things at once, it could do it. So it could potentially, with the right kind of software, that Core 2 Duo processor could run quite a bit faster than that Celeron processor, even though the clock speed is slower. Okay? So this is kind of where we've been getting into in recent years, because we kind of hit a limit with clock speed. They got to this point, I don't know, about 4 or 5 years ago, when they realized, we can't make this thing tick any faster without it burning up.
Oh, much increase the RAM.
Sure, right? So that's what I'm saying is there are other things now that they're trying to do, because a lot of your computers now actually have liquid cooling in them. Okay, for a long time they would just put a big hunk of metal onto the CPU to try to soak up all that heat and dissipate it, and that wasn't enough. Like to try to get to some of the clock speeds we're at right now, a big hunk of metal just wasn't absorbing it fast enough. So they've now put big radiators inside computers now. So like this iMac has a liquid cooling system that's just very, very similar to what's in your car. Okay, and that freaked us all out the first time that kind of came. We're like, what is this? Like, is this going to leak antifreeze all throughout my car or something, or throughout my computer? And I haven't ever heard of that happening, but I guess it's.
I've seen them blow up, but
yeah. So anyway, so eventually we hit this wall, right? It's like, okay, we can't make the clock tick any faster without it burning up because we can't handle the heat anymore. So what else can we do to make it go faster? Well, we could add more cores, right? So we can't make any single core go any faster, but we could back them off a little bit, and then we could have 2 of them, and we know we can handle that heat, so then we can make it faster that way. Another thing we could do is we could make it be more power efficient, right? So, CPUs, that work that it's doing isn't coming from nowhere, right? That ultimately electricity is involved here, and so if they could be more efficient at how it consumes the electricity, then they could even be able to add more cores, right? Because the reason that the heat thing is happening is that, as energy gets pumped into that processor, some of that energy gets used to do the work, right? But then some of that energy just dissipates into heat. That's just inefficiency that happens with every electrical circuit, right? Every electrical circuit is going to have a certain amount of inefficiency where it just takes the energy and it just makes heat, okay? So if they can make this processor be more efficient, then it'll generate less heat, right? So it's able to do more with the electricity, and that is in some ways similar to making it go faster. Okay. So then you can also adjust like the caches on it. So how big is the sort of spot on the CPU where it can store information? So how big of a number could it look at a time? And that's the difference between like 32-bit and 64-bit processors. So most of your computers now have 64-bit processors, and what they're doing there is they're saying, well, we can't make it move any faster, but we could make it look at a bigger number. So we could make it capable of counting a number that's twice as big as what it used to be able to do. And if it can look at a bigger number, then it could do bigger math. And therefore, we can have it do more complicated math. And so as opposed to having to do it in 5 steps, it could do it in 2 steps, because now it can think about it as a bigger number. Right? So these are all things that happen to CPUs to try to make them go faster. So when you're thinking about how fast is my CPU and is that fast enough, it's not really always about the clock speed. And a lot of these embedded devices that you have, like mixing consoles, now all have CPUs in them. You might be surprised when you realize how slow those CPUs are, because they optimize the software really good, and they optimize the CPU to do exactly what it needs to do. And if that computer only ever has to do that one thing, it doesn't require a whole lot of speed to do that one thing. Where you need the speed is when you have it do 20 things at one time, which is what's happening even right this second as I'm talking with your laptop. I mean, right this second, you're asking it to do a lot of different things at one time. You're taking notes. You're pretending not to check your Facebook status. You've got email pinging in the background. The clock is updating itself to tell you what time it is. Your calendar is prepping to alert you that class is going to be over in a little bit and it's time for lunch. It's doing all these things all at one time, and that's what takes all that processing power. But if it only has to do one thing, then you don't need all that speed, right? So that's why you can get away with a mixing console with a much slower processor than what's in your laptop. Because the processor that's on the mixing console doesn't have to play solitaire and check Facebook and find out, what your next appointment is and all that kind of stuff.
The Digico is just the Windows, 97?
Yeah, so that big Digico is like it's a Windows XP computer. A very simple processor. It's got what we call co-processors. It's got some extra processors in it that do all of the signal processing and things like that. But yeah, it's pretty simple. Okay, let's talk about memory. So the primary storage. Any questions so far? I'm going fast. I want to make sure I get through all this. Questions so far? Okay. Slow me down if I need to. Memory. So the CPU's job is to follow instructions. All right? That's all it does. It has no agenda. Okay? It's eager and ready to follow any instruction you give it. It loves it. I love, the CPU says, I love doing what you tell me to do. It just loves it, okay? So it follows your instructions. And those instructions get encoded into programs, okay? Here's the problem, though. A CPU can only handle one instruction at a time, okay? Every time that clock ticks, that's one instruction. It can only do one thing at a time. And usually there's a little teeny bit of storage on the CPU itself where it can store the number it's currently considering, okay? But it's a very, very simple device. It's just a very simple device that can work very quickly, okay? So because it can only really do one thing at a time, it needs some place for things to line up. So you're going to line up a whole list of things that you want the CPU to do for you, whole list of instructions, billions of them, okay? But it can only look at one of them at a time. And remember, it can do billions of these things in a second, okay? So the last thing you want is for the line to slow down. Because the CPU could be saying, hey, I'm ready for the next thing, and if the next thing isn't there ready to go, then your computer's going to be slow, right? And it's not the CPU's fault. It's just you're not feeding the instructions fast enough. So the computer needs a place to store that stuff in a way that it can get at it really quickly, okay? And that's what memory or RAM is. So RAM stands for Random Access Memory. And this contains circuits that can store program instructions temporarily. I think I might have one in here. My computer parts. Let's see. Did have one. Yes, here it is. RAM, Random Access Memory. Okay, so this little circuit board, it has these little chips. It has 1, 2, 3, 4, 5, 6, 7, 8 of them. And this says it is 256 megabytes of RAM. It's not a lot these days. So if it's 256 megabytes and I got 1, 2, 3, 4, 5, 6, 7, 8 chips, how much is on each chip? Can they do that math in their head? 256 divided by 8? 32, right? So 32 megabytes on each little chip, okay? But this fascinates me, the way this works, okay? So it's divided in equal-sized locations. It's stored, the data is stored as a pattern of electrical current, okay? So what this does is it's able to store electrical current patterns. Current, as you know, is electricity in motion, right? It's the electricity that's moving. So there's this electricity moving across this chip in a certain pattern. And so the data is encoded in that pattern, which is cool. I think that's so incredibly cool. Which is why it's so fast. Okay, think how fast electricity moves. Super fast, right? So if we're storing our data on this pattern of electricity that's moving, we could get at that data really quickly. Okay? That's why the CPU loves RAM, because the RAM is just as fast as that CPU is. And it can get at that data really, really quickly. Okay? What's the problem, though? Yeah, what happens when the electricity goes away? The data goes away too, right? The data was stored on that electrical current pattern. And if the current goes away, so does the data. Anybody heard that happen to you? Right? Happens to you all the time, right? The computer crashes, the power goes out, whatever, and you lose whatever you were working on. And it's gone forever. Why? Because at the moment you were working on it, it was stored in RAM. Because the CPU is saying, oh, okay, if that's what I need to work on right now, I'm going to put that in RAM so I can get at it really quickly. That way you're not going to yell at me when you try to type a word and it takes me forever. Okay, I'm going to put this stuff in RAM so that I can get at it quickly. So it was trying to help you, right? The CPU made that decision. I'm going to put that stuff in RAM. That's great. I love RAM. It's so fast. Okay, and then suddenly you trip over the power cord, and the electricity goes away. And boom, it's gone. The data is gone forever. You can't get it back. It's as if it never existed, right? So that's the bummer about RAM. It's super fast, and that's awesome, but it's really volatile. Okay, it has no ability to remember anything for a very long period of time. Okay? It just can't do it. So RAM is not where you want to put things that you want to remember for a long period of time. And the way you would do that, by the way, if you want to really mess yourself up, you would work on something like, let's say, a piece of music you're creating in Logic. You're working on it, and what's the computer doing as you're working on it? As you enter all this information in, you like play your notes on your keyboard and record the audio in. Where's all that data go?
To your RAM.
To RAM, right? Because the computer's like, well, that's what we're doing right now, so I'm going to put it in RAM, because RAM's fast and I love RAM. Okay? And so it's sitting there and you're thinking, great, I'm working. Oh, lunchtime. All right, I'm going to go up and take lunch. I'm just going to leave this up here. I'm going to leave it there, and it's fine. I'm not going to do anything on the computer, right? So I'm just going to leave it. I don't want to shut down because I'm in the middle of this thing. I don't want to interrupt the flow of this. I'm just going to leave it, okay? I'll leave it. I'll go get lunch, and I'll come back, and it'll be fine, okay? No. Why? Because it's stored. Your work that you've been slaving on for the last 3 hours is stored in a pattern of electrical current. Do you really want to walk away from it while it's dancing along this pattern of electrical current? No, you don't want to, because there's all kinds of things that could interrupt that, right? So what you really would like to do is if you could take that extra 10 seconds and just tell the computer, hey, I'm going to go get lunch, and I'm not going to work on this for a little while. The computer's going to say, oh, great, if you're not going to work on this for a while, I'm going to get it out of RAM and put it somewhere else so I don't have to remember it anymore. And then I can, while you're gone, I'll work on, figuring out what time it is, Okay? If you can just take a minute and tell the computer, hey, I'm going to take a break.
Give the computer a break.
And the computer's going to say, great, I'm going to move it. I'm going to go put it somewhere else. And then, then you come back and say, hey, I'm back. I'm going to work on this again. The computer says, oh, great, I'll go get it and put it back in RAM for you. Okay? That's what you want to do. Okay? If you don't do that, there's all kinds of things that could happen that would interrupt that pattern of electrical current, and then it's gone. And you're going to say, hey, computer, give that back to me. And it's going to say, give what back to you? Because the second that pattern of electrical current is gone, the computer forgets it even existed. Okay? It's gone forever. So you got to be careful with RAM. All right, some other forms of memory. ROM, read-only memory. This is, you know what that means now. Compact disk, read-only memory. Okay? Read-only memory. So, as the name might suggest, the computer can never write information to this place. It can only read information from this place. Well, so what use is it? If it can't ever put anything there, then why does it need it? Well, all modern computers include a ROM. And let's see if I can find... It's probably that. That's probably your ROM chip. Okay? ROM. Okay. What's on ROM is somewhere in the factory when this thing was made, they burned some data onto this thing. Okay? The computer doesn't even know it's a computer. Right? It really actually has no intelligence. So you turn it, just because you turn it on doesn't mean it knows how to add 2 plus 2. Okay? So what happens is there's a little bit of data that gets stored on this ROM chip that contains startup information. So the CPU is sort of programmed, and there's a little bit of data written on that says, hey, when you start getting power, go and check this spot for further instructions. Okay? So the CPU wakes up in the morning when you turn on the computer and it says, oh, okay, good morning. I'm supposed to go here to find out what to do next. Okay, and where it goes is ROM. Okay, and the ROM says, hey, guess what? You're a computer. And what that means is that you can do input, you can do output, and you can do processing, and you can do storage. And for more information about how that works, go see this other chip. Okay, so that's the ROM. That's all the ROM does. Is it's got enough of a program written on it that it tells the CPU, hey, guess what? You're a computer. And go over here for further instructions. So there's usually very simple stuff that the manufacturer will put on there because obviously you can't change it once it gets out the gate, right? So you just want very, very simple stuff there. No bugs are allowed on that program because the only way to change it is to take the chip out and put another one in. And that's a very difficult thing to do when you've shipped 1 billion of them and they're out in the world. And how do you get them all back to put a new chip in them? So they don't tend to like to put a lot of stuff on ROM, but you need a little bit of stuff on ROM. Okay? The really useful stuff is called EPROM, which stands for Erasable Programmable Read-Only Memory. So this is a lot like ROM, but it has this extra little feature where you can wipe it clean and write a new set of instructions onto it. That's not the way that RAM works, right? RAM is random access. You can go and pull anything you want on or off of it and delete little bits without deleting other bits. All you can do with EPROM is you can completely erase it and then write over whatever was there. But you can't do little bits of it. You can't say only erase this little part but leave the rest. You can't do that with EPROM. You have to wipe the whole thing. So the EPROM is where you would put things that this would be the further instructions, right? So this is startup information as well. So the CPU would say, all right, go find ROM. ROM would say, oh, hey, go find EPROM for more instructions. And EPROM would have information about what sort of input devices are available on the computer, what sort of output devices are available, what the storage situation is, and how the CPU might communicate with all those things. So that's what gets stored on EPROM. And the reason it's important to have that on EPROM is that, well, what if the hardware changes? What if you get a different sort of input device? Or what if they realized there was a bug in the way that they were telling it to talk to a certain output device? They want to be able to fix that and update that instruction set for the computer. But it still needs to be in a way that's very difficult to forget, right? Because you don't want the computer to forget that information that's on EPROM because it needs that to do everything. So you have to deliberately want to get rid of information on there. It's a very deliberate process. Anybody ever done that? It's called flashing your firmware. Have you ever updated your firmware on a device?
Well, isn't that like when you plug in an SD card or something, you tell it to reformat?
No.
Okay.
So I'm talking about firmware. If you ever had to update something called firmware, what you're doing is you're wiping an EPROM chip and putting new stuff on it, which is a very scary thing to do because what happens if you lose power in the middle of that process? You are in big trouble because maybe it says, okay, I'm going to go wipe this.
And then you lose connection,
something interrupts the process, and it's got the instructions in RAM that it's getting ready to write to that chip, and lose power and disappears from RAM, and now you've got a chip that doesn't know it's a chip, which means there's no way to reflash it. Because the only way to reflash it is to say, hey, chip, do that reflash thing. And it's going to go, I don't even know I'm a chip. What are you talking about?
Apple does a lot of, when you do an update that has firmware updates.
Yeah. Yeah. And that's a scary thing, okay? So when you're going to do something called a firmware update, you want to make sure that you've got power and a battery backup and some time. Because you don't want the lunch bell to ring in the middle of a firmware update. for example. Okay, so that's what EEPROM is doing. All right, let's talk about storage devices. So now we'll talk about the long-term repositories of data. Those are the easy ones. There's two basic ways to do this. You can store it magnetically is one way. So this stores data in particles that can carry a magnetic charge. So magnetic devices have these little flecks of metal on them, little teeny tiny specks of metal, and metal can be magnetized or demagnetized. And if you can cram enough little specks of metal onto something, you can store a pretty big pattern of magnetized versus not magnetized, which is a whole lot like 0 and 1. Okay, which is how computers think, 0 and 1. So stores data in particles that can carry a magnetic charge. This is like your hard drive, your hard disk drive. Okay. Floppy disks, you remember those? Those were magnetic back in the day. Tape drive. You ever seen a tape drive? Yeah. They used to use those on servers. So you can go buy data tapes that are like these big cassette magnetic tapes, and they can store a ton of data. They're not very fast, but you don't need a backup to be fast. You just need it to remember something for a very, very long time. Tape's really good at that. So magnetic. So that's cool, right? Magnetic. That works. It can, that magnetic charge will theoretically last forever, right? Until you somehow interrupt it in some way. But you have to do something to make it not be magnetized anymore, right? So magnetic storage, it's good. It'll remember something for a very long time. Can you think of ways you might screw that up?
Put another magnet close to it.
Yeah, if you got that too close to another magnet, you could get in trouble. So we used to run into this problem a lot in sound because we would always want to hang our monitor loudspeakers up right next to our computer. Why? Because it sounds really good. But what's inside this box? A couple of really big ones, okay? And then you stick them right up against your computer. And it would all kinds of crazy stuff would happen to your computer. Your screen would freak out, and your data would get corrupted, and all kinds of things could happen. So now they make them, like this one I believe is shielded. They actually put some magnetic shielding around it inside the case, so that the magnets in the little speaker doesn't get out of your stuff that is storing your data magnetically. The classic thing we used to be able to do is that floppy disk, you take it out and you go set it up on top of your monitor. Well, what's that big CRT tube monitor? What's that doing? Radiating all kinds of electromagnetic energy. Okay? And it would just scramble every little particle on that floppy disk, and you'd lose everything. It was a really great way to wipe your disk. Like you just scrape it across your monitor a couple times and it would go away. So you just got to be careful. If you're dealing with magnetic storage, you want to be careful around magnetic fields. Okay.
What would be the distance you would require between speaker and...
Yeah, I mean, it depends on the size of the speaker, the size of the magnet, how much shielding there is in between it. I mean, these days, it's usually most things are shielded pretty well. But you want an air gap for sure. That's my rule of thumb, is air gap. But we don't run into it too much because a lot of stuff these days is not stored magnetically anymore. True hard drives are, but solid state drives work a little bit differently. It's like it's storing a pattern, but it's not exactly magnetic. I don't actually understand entirely how it works. It's kind of magnetic, but it's kind of not. So it's nowhere near as volatile. It's very cool. But the reason they call it solid state is because it doesn't have any moving parts. I don't know if I've got one in here.
It's all just circuits.
Yeah, so that's why it lasts so long. Let's see if I can find my hard drive. I don't have it, but so what happened on the hard drive is you've got this little platter, they call it, and all the little specks of metal are glued to it, and then you have this little wand that moves around. Okay, the little things platter spins and the wand moves around. It has to read all those little specks of metal to try to figure out whether they're charged or not charged. So what happens is either the little motor that spins the platter around will stop spinning, or the little arm that moves around will stop moving, and then your hard drive's dead. The data's still on there, but you just can't get at it.
Are you saying it's a new thing or an old thing?
That's if you have a true hard disk drive, like you probably have, that's probably on your laptop. Is a hard drive. I have two here. So the external drives that I have here. Oh, I've got.
You're saying the difference between that and like solid state or something?
So this one is a solid state, no moving parts. This is hard drive, moving parts. Okay. Interestingly enough, though, the solid state, although my understanding is there is still some magnetic stuff going on there. It's nowhere near as sensitive to magnetic fields as the hard. So it's really tough to erase these things. You have to really want to do it. You have to have electricity to do it. Okay, this is what it boils down to. A magnet is not going to erase it. A magnet coupled with some electricity can. Okay, so hard drive though, which is this other one, that has the moving parts. It's got little platters in there spinning around and little wands. So your laptop probably has a hard drive. Yours probably has solid state.
It's a solid state.
Your twos probably have hard drives.
I don't know.
So the good news about the magnetic hard drives is they remember stuff for a pretty long time, and they're relatively cheap these days. They can store quite a bit of data, but there is that moving parts kind of problem. And in most cases, the hard drive manufacturers are warranting these things for about 3 years. And they'll say, we're pretty confident that all those parts will stay moving for 3 years. After that, not so sure. And sure enough, about every 3 years, my hard drive stops moving. So that's why I have two. So this solid state one can't store as much, but it's faster. So whatever I'm currently working on right now, I put on the solid state disk. And whatever I was working on last year that I might need to get at, like maybe I need that dog bark from a while ago, from that 2 shows ago, I put that on here. I carry that around with me. I have my sound effects library on here. The theory being that of the two things, the one that's more likely to blow up and lose all my stuff is the hard drive. So if the hard drive went down, I don't lose anything that I'm working on right now. So it doesn't impede my ability to do my show today. It just impedes my ability to find the dog bark from 2 years ago. And I can sort of live with that. That's a level of risk I'm willing to accept. And then after 2 years or so, I'll take it off of there and store it somewhere else on an optical storage, as we'll talk about. Because it's like, well, after it's been 2 years, presumably I've invented a better dog bark now that I'll be using. So I don't need that one anymore. Okay. So let's talk about that optical storage now. So optical storage is the data is stored as a pattern of what they call pits and lands. So it's like a little dent. It's like a little piece of foil that's either dented or flat. And a laser will shoot at that thing. And the laser figures out how far it had to go before it hit something. Okay? So when it hits a pit, it travels just a little tiny bit further than it would travel to hit the not pitted part, the land. Okay? And that's sort of like 0 and 1. Okay? So pit or land, 0, 1, 0, 1. Actually 1, 0, I think. I believe the pit is a 1, the 0 is the land. So good news about optical disks. This is like your CDs, your DVDs, your Blu-rays. These are all optical based. Okay. Good thing about them is they're not as fast as the magnetic disks, but they don't break. There's nothing about them that would stop moving. There's no moving parts on an optical disk. There's moving parts inside of the device that reads that disk, right? But if the drive fails, the disk does not, and you just get a new drive and you get your data again, right? It's not so true of your hard drive. If that hard drive stops moving, if the little parts inside there stop moving, the little platters are still there, and your data is still there, but you can't get at it unless you pay some company thousands of dollars to take your drive apart get those platters out, stick them into a working mechanism, and then they can do it. But it costs you a lot of money. You got to really want what's on that hard drive to pay that kind of money. So the good news about optical disks is they're pretty reliable. Okay, there's nothing that's going to fail on that. Okay, the only thing that's going to fail is the hardware that lets you read it, but that's okay.
The optical drive.
Yes, the optical drive. You just get a new drive, right? It sucks, but that's cheaper than paying somebody thousands of dollars to take apart your hard drive and reassemble it into a new one. Okay.
Can you rewrite that? The pits and lands?
Some you can, yeah. So like a CDRW is rewritable. So what it can do is it can turn a pit into a land. The laser is able to manipulate that surface in some way to rewrite it. It works a lot like EPROM in the sense that it's not random access. You can't say, oh, go like right over this one little part, but leave the rest of it intact. It doesn't really like to do that. It likes to kind of do it all or nothing. But the good news about optical storage is it's very high capacity. So you can store an awful lot on a single optical disk. The CD, which was the CD-ROM, whatever, that was like 750 megabytes, which was a lot back then. And now, like a Blu-ray disc, a dual-layer Blu-ray disc is like, what, 30 gigs or something like that? I mean,
32.
It's a lot.
Except your computers can't read Blu-ray yet.
Yeah, so I mean, you would have to have a drive capable of reading that disc that has the right kind of laser in it. But it can store a lot of stuff, and it'll store it for quite a long time. I mean, most manufacturers of optical media now, they're warranting that for 100 years. They're saying you put something on that disc, you should be able to come. We can pretty much guarantee you can come back 100 years later, it'll still be there. I don't know that company will still be in business 100 years later to honor that warranty, but they've done the sort of accelerated life testing and everything, and they sort of think, yeah, that's if you take care of it, you store it well, you keep it in a controlled environment and everything, yeah, that'll last for a long time. So that's good. If you want something, you want to remember something for a really, really long time, put it on an optical disk, not a hard drive. Okay, hard drive will remember it for a while, up to 3 years. But after 3 years, the hard drive is going to start getting awfully forgetful. Okay? So if you want to remember something for more than 3 years, put it on an optical disk. So this is like CDs, DVDs, Blu-rays, stuff like that. Okay? I have my safe in my office, that I crack the combination to. And what I have in there, if you open up that safe, the only thing I have in there is a spindle full of optical disks. You know what those are? Old shows that I worked on, right? So anything that's like more than a couple years old that I don't want to put on my hard drive, I burn it onto an optical disk, and I stick it on that little spindle and I put it in my safe. And I think, great, there you go. If I ever need to get that show that I did 10 years ago, it's on an optical disk somewhere, and presumably that disk is going to remember it for another 90 years, and I'm cool with that. I think 100 years from now, I'm probably not going to be a sound designer anymore. So I'm not going to really need that show. I'm not going to need that dog bark from 1998. Okay. All right. That's all the hardware stuff. Any questions about that? All right. Let's talk about software. So none of that hardware is very useful without software. Okay. In fact, in the early days of computers, we had a lot of hardware, but they couldn't do anything. The computers couldn't do anything because nobody could write the software for it. When we went to see the recording studio over in Chapel Hill, Manifold Studios, Michael Tiemann. So you know how he made all his money? He wrote the first C++ compiler.
Seriously?
Yeah.
Wow. Okay.
The GNU C++ compiler, that's his. He wrote that.
Wow. Okay.
So what he did was he is the vice chair of our board of trustees on School of the Arts here. Okay, and then he built this amazing recording studio. But he wrote some software that translated, things that human beings would want to do into machine code that a CPU could follow. So binary. So he wrote a piece of software that does that, and it's now like every computer program ever. Now, it runs through that compiler. Or some iteration of that compiler, okay? So that's why he could afford that big API console, right? Now you understand why his recording studio is so fancy. Exactly. So the software is the bridge that converts ideas and instructions that people understand into instructions that a computer understands. Okay, that's what software does. And this is the part I want you to remember. A computer can do anything that you can teach it how to do. Okay? So you teach a computer to do something by writing some software. You create some software that's some instructions. And this is my rule of thumb. Never ask the computer to do anything for you that you can't already do for yourself. Okay? That's the recipe for disaster with a computer. If you start asking it to do something for you that you don't already know how to do yourself, that's when you're going to run into trouble. Because the computer can only do things that you can teach it how to do. It's just that sometimes the computer can do it faster than you can. And that's why you would use the computer, is because it can take something that you already know how to do, and it can do it faster. Okay? For example, Jim and Corey over here are writing, and Lisa are writing, they're taking their notes, right? They know how to do that. They can write those words. They can write it down on the paper. Everything's great. They're capable of doing that. Jay Shell and Tracy are over here using a computer to do the same thing. It's able to do it a little bit quicker. If you're a really good typist, you could actually type a little bit faster than you could write. The computer could spell check that for you alive as you're going, faster than you could, and autocorrect it in some cases faster than you'd be able to. Right? So that's why you would want to use a computer to do that. If you're a fast typer and you like letting the computer handle some of that work for you, then it could go quicker. But if you don't already know how to write those words, you're going to have a tough time getting the computer to do that for you, right? Because you have to be able to tell the computer, okay? So let's talk about software. So we need to understand how a computer follows instructions. And we use a really simple example here. Let's say we're going to make some French toast for breakfast. And we gave you this recipe card. So if I gave you this set of instructions for French toast, is there anybody who feels that they could not make French toast from this recipe? Is this sufficient instructions for you to make? Okay. But you feel that there's a reasonable expectation that you'd be able to make French toast from this?
I don't have a pan. There's no pan.
You don't have a pan?
Yeah, there's no pan.
Okay. Well, we're getting now to the stuff I'm interested in. Okay. So so human beings, we could infer a lot here, right? We could infer that we're going to need to use a pan, right? And we could infer the fact that that pan's going to need to get hot somehow. Okay. And we could infer that a bowl would be involved, right? And something to beat those eggs with. We could infer that. These are all kinds of assumptions that we would make based on our previous experiences and things like that. A computer will make none of those assumptions. Okay? So if I were to give these instructions to a computer, the computer is going to have all kinds of problems with this. Let's think about some of the problems that the computer is going to have. Well, it's not going to know that a pan is involved, right? So it may, when we say fry in the butter, it may fry it on the table or on the floor. We didn't actually say what to fry, did we?
No.
So it might fry the eggs.
Eggs probably still have shells.
Yeah, we never said to discard the shells, did we? We just said combine the eggs.
Slightly beaten.
And it would be perfectly within the instruction set if it just mashed those eggs together, shells and all. Okay. Yep. And slightly beat them with what exactly? What am I beating them?
What happens when you smash them together?
Right.
What?
Okay. We didn't specify what mixture is. Okay. What is it dipping the slices of bread in?
Where?
We also, the computer would technically be correct if it took all 6 slices of bread and dipped them in, assuming it knew what the mixture was. It could take all 6 slices of bread, dip them in that mixture, and pull them out, and it would be technically correct. But that's not exactly what we wanted it to do, is it? We wanted it to take one piece, dip it in there, put it on the pan, right? And then do that again, right?
But it doesn't know there's a pan.
It doesn't know there's a pan, right? So there's problems with this, right? all kinds of problems that if you were to ask a computer to do this, this is not sufficient enough information. So I love this little quote here from the American Library Association when they saw the UNIVAC computer, which is this early computer back in the 60s at the World's Fair. And they said, "The computer is only a fast idiot. It has no imagination. It cannot originate action. It is and will remain only a tool to man." And you know what? They were exactly right. I mean, that is exactly what a computer is. It is a really fast idiot. Okay? There is no agenda. The computer doesn't hate you. It makes no decisions on its own. Right? All it does is does what you tell it to do. Very fast. Okay? So here's another version of French toast. This is where this is closer to what we would need here. So I've separated our 4 steps into some sub-steps. So I'm saying, all right, step 1, prepare the batter. So we got this thing called batter, and you're going to make it using these instructions. Crack 2 eggs so that the whites and the yolks drop in the bowl, and you're going to discard the shells. Okay? Great, now we got rid of the shells. And we've indicated there's a bowl involved, right? Okay. B, beat the eggs slightly with some sort of device, right? A fork or a whisk or something. Okay? Great, so it's doing that. And now you're going to put in these other ingredients. Okay? So mix in the vanilla, the cinnamon, and the milk. Great. Now we should have successfully created some batter. Okay? Step 2. Place a small amount of butter in a frying pan.
Yeah.
And place it on medium heat. Okay? Well, we would, this is, again, there are some assumptions here, right? We'd have to define, where the heat source is. And there's an input or output device involved there, right? So we'd have to have that device, but presumably there's some firmware involved in telling it what heat it is, okay? All right, so now the pan's heating up. Step 3, for each of the 6 pieces of bread, do the following things. So this is a loop. Okay, so for each of them. So first piece of bread. Okay, great. I got the first piece of bread. Dip that slice of bread in the stuff. Okay, great. Okay, I did that. Now, for each of the 2 sides of that piece of bread, here's what you're going to do. You're going to place the bread on the pan with this side, the side you're looking at, down. Okay, great. You're doing that. And now you're going to wait 1 minute. And then, when that 1 minute is up, you're going to look underneath of it and see what color it is. And if it's any lighter than golden brown, repeat that step. And what was that step? Wait 1 minute, and then look again. Okay, so it's going to keep doing that over and over again until at one point it's going to look at it and go, golden brown. And then it's going to go and repeat step B, right? Or step 1, B1. Which is, now I got to do it for the other side. Other side, wait 1 minute, look, wait 1 minute, look. Let's keep going. Oh, golden brown, great, done. Slice 1 complete. Okay, slice 2, all right? And it's going to keep going that until it's done all 6 of them, because we said do it for 6. And so on and so forth. Then the fourth thing, we're sort of punting here at the last step. There'd be a lot more involved there. But okay, so hopefully you're getting some of the ideas. Now, assuming that we had the appropriate input and output devices to recognize the color golden brown, recognize medium heat, output devices that could allow it to manipulate a whisk, so on and so forth, then a computer ought to be able to do this. We would need to get even further into detail, though. But this is how you would teach a computer how to do something. You make no assumptions. Okay? Computers do what you tell them to do, not what you want them to do. And if you take nothing else away from today, I want it to be that. Computers do what you tell them to do, not what you want them to do. Every time. They will always do exactly what you tell them to do. And if that wasn't what you wanted it to do, then you didn't explain it well enough. You need to tell it something else, because it will always do what you tell it to do. Okay, real quickly, types of software. Application software, system software, and firmware. Okay, these are your three types. Firmware, this is software, we talked about it briefly, this is software that's embedded in a device, usually written on like an EEPROM chip. The firmware teaches the hardware how to communicate with the other hardware. So this is how the CPU knows how to talk to the input devices and output devices and storage devices. Usually this is found on a ROM or an EEPROM chip. Okay? That's firmware. Very important stuff. Every once in a while it has bugs and you've got to redo it. Okay? Sometimes you might refer to firmware as something called a BIOS or open firmware or EFI. You ever hear those terms? They're talking about firmware. Okay? Your Macs all have EFI on them now. If it's a Dell computer, it probably has BIOS. Okay, but these are all forms of firmware. Okay. System software. So this is also called the operating system. So this provides some sort of user interface to the hardware. So this gives you, the human being, a way of interfacing with the hardware in some way that makes sense to you, and it also has some ability to launch other instructions or other programs. So it's this base subsystem that gives you a way to interface and some way then to manipulate and launch your own instruction sets. So examples of system software are things like Windows, that's Microsoft's operating system. Mac OS X is an operating system. Linux is an operating system.
It's kind of similar to like the transport on Dimitri or whatever. Like it would be,
Yeah.
As we program it until that's our operating system.
Yep, exactly. Okay, so that's your ability to manipulate things. It gives you some ability to manipulate the computer and its hardware and run instructions. Application software are those further instructions. So this is where this application software is software that employs the capabilities of the computer to do some sort of specific task, such as type my notes for me, or draw this picture for me, or edit this piece of sound for me. That's application software. So software written for a specific application. And those are separate instruction sets. You can create your own, or you can buy other people's instructions. Either way. Sometimes it's fun to make your own. I like making my own sometimes. It's fun. You can tell a computer to do exactly what you want it to do. Okay, so those are your three types of software. It's important that you understand which one you're working with at a given time. If you're having a problem with the computer talking to your mouse, that's probably not, odds are it's not a problem with your application software. That is not a problem with logic. That's either a problem with your firmware or your operating system. It's one of those things. So that's just an example. What's that?
Or just turn on.
Yeah, or something stupid like power or whatever. Okay, that's it. Questions?
Yay, computers!
That's fun, right? Hopefully you learned something interesting.
Podcast.
Yeah, so I just recorded it. I'm going to stop it now.